Hello CS302 class. Here's our assignment 4, which is going to be, once again, performing a sorting algorithm. And of course, we're going to have our friend Mr. Meeseeks here help us out with this sorting algorithm. So we're going to be performing selection sort. And we didn't really cover this in our course, but it's a very simple algorithm to sort of write or think about. So for selection sort, the way it works is you basically have to do a linear search through the list to find the largest element in the list. And you're going to find that largest element and sort of store its index in the array. And you're going to swap it with that last element in the array. And then you do the same process again. You find the max element again, but this time you find the max of all the elements except that last element you swapped with, is the idea for selection sort. And you keep doing this until you have a sorted list. So this is actually a relatively trivial sorting algorithm. So of course, you can Google this and of course find a link on Geeks for Geeks, which will really give you some really good insight on this algorithm. And we're going to basically use this parallel approach using this sort of tournament algorithm to be able to somewhat enhance the runtime needed to find that max element and insert it to the end. Also with selection sort, you could do where you find the smallest element in your list and then insert it to the front, or you swap it with that front element. And then of course you can find the next smallest element and swap it to the second position of the array and so forth. Either way works. And you want to, of course, sort this in ascending order. So that's basically just the whole idea of this program. So let's go ahead and now talk about the details of implementing this algorithm. So before I go into the actual details of the algorithm, let's first go over the input and output. So the input's pretty trivial. You're going to read in a file name, and you're going to open up a file stream, and you're going to read in a bunch of integers from a file, and of course you can store it into a vector. So since it's already going to be a little bit of a challenging assignment already as it is, why not make it simpler by using a vector? So you can just read a number from the file, and then call a vector's pushback function to insert element into a vector. So that part is pretty simple. And of course the output will be just outputting a sorted array or sorted list. And of course, on code grade, I'm going to have it skip any white space. You want to make sure that you have some type of a separator between each number. So a new line, a space, a tab, whatever you have to do to have some separation, so then code grade can correctly test your output. So I have the complete sort of contents of main. It's going to be really the algorithm for this program. I have all the details here. Of course, we're going to have to use a somewhat of a thread pool. It's not going to be a true thread pool really, but we'll kind of call it a thread pool. So we're going to have a list of threads. We're going to spawn threads. We're going to join them and keep doing this process again and again. So we're going to implement this sort of these rounds. It's almost like in a tournament, like I guess any kind of sporting event or NFL playoffs. You have these tournaments. You have the wild card round, division round, championship round, and of course you have the Super Bowls. You have these sort of tournaments, and after every single level, half the teams are eliminated from our tournament. So basically that's what we're sort of going to be doing using threads. So you can of course read through all of that, or not. But I'm going to go ahead now and just do more of a visual representation of what this content in this PDF is supposed to demonstrate. All right, so this is going to be our data structures used in this program. So I'll go over, max's list in a second. I think that's the proper way to have a plural. So not one, but multiple maxes. I think that's a proper spelling, maxes. But if it's not, then just it's maxes. So the plural of max or maximums. So we're first going to have this list right here, which is going to really just be a vector of integers, and we're going to have n elements in this vector. So our size is n, but it goes from 0 to n minus 1. So of course, the standard selection sort, the way it works is you're going to first find the max element in the list. So let's say, our max element happens to be right here. That's where our max element is located. So you want to actually store the max and also know the index of where this max element is. And once we go through a whole list, we run that typical 135 method of doing a find max. We find that this element is going to be the biggest element in our list. So then we're going to basically just swap it. We're going to swap it with that rightmost position. And of course, what will happen is this element that's right here, these elements are going to end up swapping. I'm going to go ahead and just denote this violet, or I think violet or purple or pink box right here. So it's going to end up going right there. So now what's going to happen, you have to again do a find max, but this time the max element is going to be in this range without that pink box element. So of course you go through this again. Let's say maybe this time our max happens to be here. You're going to swap that into this position, which means now we're going to have this setup. So we're building up our max, our sorted array in reverse essentially. So you have our max element, our second max element, and so forth. Now also, alternatively, you could do a find min instead and put the min element into index 0, and then the next min goes index 1. So you can do the same thing but in reverse, where you just find a min and then you just insert it to index 0, then you swap it to index 1, and so forth. It's up to you how you want to do this, but either approach is still essentially selection sort. So this method works, but of course, just as repeated, we want to use threads. We don't want to do this in parallel, or sorry, we don't want to do this sequentially. We want to do this in parallel. So we're going to have a max number of threads. So we're going to use that function. I think it's thread hardware concurrency, which I mentioned in class. That's going to give us the max number of threads you can spawn on your system concurrently. Now, of course, as mentioned in class, if you spawn more than that many threads, it'll still work, but then the operating system has to spend more time constantly swapping threads in and out from the waiting sort of state to the working state. So we don't want to overload the operating system, so we're going to be careful and not spawn too many threads. So what we're going to do instead is we're going to divide this list into pieces. So I'm going to have this one be T1. So we're going to essentially break this list into these blocks. And the sizes, well, it depends on how many elements we have. I think I'll just do this. This will be an extreme case. But anyway, we have T1, T2, T3, and then of course, I'm going to call this one TM minus 1. So in this case, M is going to be the amount of threads we can spawn, and T1 will be thread 1, thread 2, thread 3, up to thread TM minus 1. So what's going to happen is we have to spawn a thread and use that thread vector, that vector of threads, which will be our quote-unquote thread pool. We're going to assign a thread to a portion of the list. So all we have to do is create a thread function and simply pass in the left and right endpoints. So the thread T1 knows the range of elements. It's going to have to do a linear search to find that min or max element, depending on if you're doing that min approach or max approach. The same thing for T2, give it the proper indices and so forth. So you have to go ahead and compute these indices. You have to use a loop to constantly just, this loop will basically spawn M number of threads. Each thread will assign the correct sort of indices. So I don't think this would be too complicated. So what's going to happen is we're going to basically just then have each thread do a linear search to find that max element. Now each thread is going to have the same size list. It depends really on how many threads we have and how big our list is will determine how big each chunk of these will be. Now, obviously, the only thread that could have less work to do would be the last thread, because obviously there could be some carryover. So we could do is we can spawn some threads, and we can't divide it evenly up. Let's say, for example, we had, if we had, let's say, 25 elements and only 4 threads, each thread would get, size 5 blocks, and then the last thread would get a size 4 block, right? So you can't all divide it evenly every single time. So anyway, once you go ahead and you find the maxes of each one of these, you want to insert them into this maxes list. I'm actually going to maybe I'm going to have it as actually m-1, so it's less writing. So I'm going to have m-1, m meaning the max number of threads you can spawn. So each of these threads. So let's say T1 happens to find the max element at some position. Let's say it happens to find it right here. I'm going to call this maybe just M1 for right now. You want to push M1, and I'm going to go ahead and call this maybe just also I1. So you want to actually store the index also. So I'm giving a little bit of help away, but it's all right because for 302, having a thread program is a little bit difficult. So I'm trying to give as much help as possible. So we do that. And then thread T2, so remember, these are all going to be doing in parallel. They're doing it in parallel, so you have to essentially insert each of these in here. Now, let's say T3 actually could find the max element before T2. So then maybe M3, the max of the third thread, writes its value right there. So you're going to actually push back into this vector. But here's an important fact. So in this situation, where you respond to threads to find the max in each sort of sublist of our main list, there's no overlap because thread T1 is going to process this part of the list, and thread T2 will process this part, so no overlap happens. So, and they're just only reading elements in the array. So there's no race conditions that's going to happen here. But if you have multiple threads, pushing results into this vector, into this, looks like a two-dimensional vector of some sort, has these max elements and their indices in the array. You want to be careful because two threads at the same time might try to push into this. Or let's say, okay, how about I go ahead and let's say you want to be clever and say, okay, I'm going to go ahead and just size this vector to be m-1 or m elements from the get-go, and use a counter to increment by 1 each time and assign something here. Same problem will happen because two threads at the same time could try to write to an element and they both will increment this counter by 1. So writing to this array will cause erase conditions. You may want to use that locking mechanism to make sure you don't have any issues with this. But anyway, in any order in particular, let's say you have M4, I4, and then of course, I should probably keep like this. We're going to have M M-1. This is really confusing, but I hope you understand that this is going to be just the last, max found. So of course, this list is going to have exactly max threads amount of elements. So we're going to have the max element along with the index. So we know once we find the final max, we know which index of the element in this array we want to swap to the end. So that's our first phase. So you first wanted to find these maxes. So now let's go ahead and discuss our next phase of this tournament algorithm. All right, so let's go ahead and now talk about this tournament algorithm. So basically here, so we can assume that in this maxes list, we're going to basically have exactly max threads or m amount of elements. So in this next phase, we're going to want to spawn half the amount of threads. So not going to spawn m threads, which is the max our system can handle, but instead spawn m minus m over to m divided by 2 number of threads. And here's the reason why. Because what's going to happen is we're going to have this contention. We're going to have this tournament where Team 0 and Team 1 is going to compete for which one is the largest. And of course, Team 2 and Team 3 will compete. So every adjacent sort of pair of elements are going to compete, basically. So in this example, I kind of had more or less 8 threads I was able to spawn. So originally, I created 8 max elements. I spawned only 4 threads. So we have in T1, we're going to compare these two adjacent elements, to which one is the max of the two. Then T2 will compare these two maxes and then figure out the max of the two. So, I mean, it's up to you how you do this, but you have to find, you can maybe have another vector if you want, but I would just suggest maybe just sort of in this vector. So let's say M3 is the bigger element, then what I would do is I would actually sort of wipe this out and override this to be M3 I3. And over here, same thing. So between T2 and this T2 thread, these two elements, let's say you have M4 and let's say we had maybe like, let's say we had M5, I don't know, an I5. Let's say if M4 was the bigger one, then we're going to clear this one out in some way and store this max element right there, just like this. So just to kind of have all these stored some way somehow. So we could actually, in fact, maybe just somehow clear out one of these spots. Maybe just clear it out actually would be even better. I don't know. It's up to you how you do this. I did it like this, but you of course can just clear out which one is the smaller, or you can override into a certain position. And eventually you're going to have exactly just, we're going to have at the end of the day, so I'll have, maybe we're going to have, let's say, M6, I6. I'll have M7, I7. We have this scenario now. So in main, we spawned essentially M over 2 threads. And now, in main, we're going to spawn threads again. So this is going to be our tournament. So this is going to be done all in a loop. We're going to basically first spawn M over 2 threads like we did right here. And now we're going to spawn M over 4 number of threads. So we're going to have just, in this case, only 2 threads we're going to have now. T1 and T2. So the first loop in main, you spawned M over 2 threads, and then you just sort of picked adjacent elements to compare with, which one's the bigger of the two. So it's like when you have 2 teams playing each other in the playoffs. So we had 8 teams originally, now we have 4 teams left. So we're getting, no, sorry, we had 8, now we have 4 teams, yes, okay. So now, same idea. Among these 4, well, T1 will compare M3 and M4. Let's say M4 is a smaller one. Well, then I'm going to go ahead and overwrite, put M4 over here, I4 over there. I'm going to clear this out. Let's say among M6 and M7, M7 was a larger. I keep saying smaller, my mistake, I'm sorry. I think I got, okay, so larger. So the larger one will go over here. So let's say M7 was a larger one, then we're going to overwrite this position. And the last, let's say M4 was larger among M4, and I think M3 we had. So we write M4, we overwrite that over here, and then M7 overwrites over there. So now, going back to main, now we spawn M over 8 number of threads. Or other words, we're going to spawn just half the number of threads. So we're only going to have 1 thread left. And then we go ahead and compare these ones. So let's say M4 is the larger of the two. Then index 0 now is going to have our final max element. So we know the actual value, we know it's indexed in the array, so we can go ahead and simply just take this element at whatever position it is and simply swap it right here to the end. Like that. And then same idea, so that means now we finished one step. We found our first max, stuck it to the end. So now we're going to do, so I'm going to go ahead and sort of redraw this. We're going to basically now do the same exact process. We're going to now just again spawn the max number of threads possible. This is again not very well drawn to scale, but it's okay. And of course we have this, then we have maybe this, I don't know, Tm-1. But notice that last element at n-1 is not going to be in contention anymore. So same thing happens. We're going to fill this array with all of our maxes found. We're going to fill this array with all these elements and with their indices. And again, we're going to, so this is a case where I happen to have 8 threads. Why not? We have 8 threads. So again, we're going to do the same process. We're going to have, so our first loop in main was to spawn 8 or m number of threads and pass in the correct ranges, and then find a max in each of these using a regular linear type of traversal, and write each max element found with its index into this array. And again, same idea, we're going to spawn half the amount of threads once again. Things like this. And we just compare the two elements that we're going to look at, And the bigger one, we're going to have to somehow store it into this vector. So I actually would always, in that leftmost endpoint in T1, that's where I would put the max in there. And for T2, leftmost endpoint. So really, this is going to cause a different function. So you're going to have really one function. So you may have to have two thread functions possibly. So two thread functions might be necessary. The first one's going to be doing this. So the first thread function is going to, so the first thread function is going to be just simply earmarked to do that linear search to find the max in that list. And our second thread function is going to basically be done to implement this tournament algorithm. So here, there's no loop that will be done in this second thread function. It's going to, So the second thread function will not have a loop. We're only going to compare two elements, but we're going to have multiple rounds. So we first have our wildcard round and our divisional round, championship round, then we have our Super Bowl at the very end. So it's sort of like that. So we have our first round, we spawn 4 threads, and of course we're going to have that. We have to sort of figure out what are the two endpoints, what are the two elements we're going to be comparing against. The next time we're going to have half of those, so m over 4 number of threads. And we have to sort of figure out what are the two elements, what are the two adjacent elements that are going to be in comparison. So we have to compare essentially. So after we do all this, the next step, remember, we have to go ahead and have T1. We have to compare it with, with these two elements. Because index 0 is the max found for thread 1. Index 2 was the winner among index 2 and 3 in this max's list vector. Now, you don't have to do it quite like this. This is how I did it, but it's up to you. We had to find a way to somehow denote which are the two elements that won the last round that are still in contention to compete with each other to go on to the next round of elimination. So basically, that is this sort of algorithm in a nutshell. So we're going to have a loop that runs n number of times, the outer loop. And in that loop, our first phase will be to spawn m threads to find these maxes. Then we're going to have another loop within. So we're going to have two different loops in our main outer loop. And this second loop will implement this tournament algorithm. Then we insert the max over here at the end. And then, of course, next iteration of our loop, we spawn m threads to find the maxes. And that second loop within that mega for loop will be to implement this tournament algorithm. So that basically is sort of the overall algorithm here. So yeah, so I think with threads is a little bit complicated, especially in 302, but it does give us an idea of how threads work. So you may have to work with multi-parallel programming a little bit in your later CS courses. This is sort of a little bit of a warm-up to how to handle multiprocessor programming type content. So anyway, now let's go ahead and go over some final final remarks of the assignment. Okay. So obviously, you can use global vectors because you're going to have multiple threads and you're going to be sharing a common vector. So obviously, that list vector of integers and that maxes list I also used is going to be global vectors because it makes the process easier. Because passing any type of variable by reference to a thread is a problem. You can pass so you can, when you're doing your actual parameters, you can pass a reference and then have a pointer as your parameter type for a function. But if you try to pass just by reference, it will not work. So a simple way is just simply to have a global vector and then pass in indices that tells this thread to which part of the vector is going to be handling. So also, do not spawn more threads than we can run concurrently. We want to write this to be a bit more, nicer. We don't want to have the OS do too much work. We want to make sure we don't overspawn, so OS will have to do extra work. Now, the other thing is if you're going to be using a Linux-based system, you have to use this -pthread compiler flag in order for it to work, because the thread library is not going to be recognized by the compiler in your code unless you include this flag. Now, if you're using a Mac terminal, you can actually not, you don't have to include that pthread flag, but you have to include this C++11 flag, because I think on Mac terminal, it doesn't automatically compile in C++11, and a thread library is in C++11. So, but you can actually include both of these flags, and it won't cause any harm. So if you're on a Mac or Linux, if you use both pthread and this other flag, you're okay. But really, for Linux, you have to use this, and for Mac, you have to use this. But if you use both for for either system, you're fine. Now, for last very important want to mention here, I'll probably mention this in class as well. If you are going to use the school server, do not use Sally for any circumstance at all. So the issue is that for multiprocessor programming, if a thread, let's say for example in your thread you have infinite loop, or a thread didn't join properly, that thread will keep running on the system, and Sally doesn't have a way to be able to terminate any running away threads, but Cardiac does. So you don't want to use, so if you use Cardiac, you're safe. You're not going to cause any potential issue on the server. But otherwise, the server will crash, and then, it will be bad. So use your own local system. If you do use a school server, please use Cardiac. It's the same login, same password as you would if you use Bobby or Sally. So really, there's no reason, there's not any extra overhead. So please use Cardiac if you're going to use a school server. And that's pretty much the complete sort of description of this assignment. Hopefully it did sort of help you. I guess happy coding, and as always, take care, you guys, and stay safe. So take care for now.